Hello everyone. Welcome back to class 11 Mathematics. Today, we are entering one of the most fascinating parts of probability, event equations. Let's start with a question. When you toss a coin or roll a dice, what exactly are you predicting? You're actually predicting events. When you say, I'll get heads, or I'll roll a 4, that prediction is an event, a specific outcome or a group of outcomes from all the possibilities of an experiment. Mathematically, we call the set of all possible outcomes the sample space, usually denoted by capital S. And any subset of this sample space, whether it's one outcome or many, is called an event, often written as A, B, or C. So, if we roll a dice, the sample space as equals 1, 2, 3, 4, 5, 6. The event, getting an even number, would be A equals 2, 4, 6. The probability of an event is given by P of A equals N of A divided by N of S. That is, the number of favorable outcomes divided by the total number of outcomes. So yes, every event is simply a subset of possible outcomes that we care about. That's where all the magic begins. Now that we understand what an event is, let's explore its types. A simple event contains only one outcome. For example, rolling a 3, just one possibility. A compound event contains more than one outcome, like rolling an even number, 2, 4, or 6. An impossible event can never occur. For instance, rolling a 7 on a standard die. Its probability is 0. A certain event must occur. When you roll a die, you will definitely get one of the 6 numbers. So its probability is 1. Two additional important types. Mutually exclusive events. When one occurs, the other cannot. For example, getting heads and tails on the same coin toss. Exhaustive events. Events that together cover all possible outcomes. Remember, mutually exclusive events never overlap, and exhaustive events cover the entire sample space. Now let's explore how events combine mathematically. The algebra of events. A union B means event A or event B or both occur. A intersection B means both events A and B occur together. The complement of A, written as a dash, means A does not occur. Everything in the sample space except A. Now the most important formula. P of a union B equals P of A plus P of B minus P of A intersection B. This subtraction avoids double counting outcomes common to both events. And if A and B are mutually exclusive, then P of A intersection B equals 0. Simple, logical, and mathematically precise. Let's examine how events are connected. Independent events. The occurrence of one does not affect the other. Example, tossing a coin and rolling a die. Condition, P of A intersection B equals P of A multiplied by P of B. Dependent events. One event influences the other, like drawing two cards without replacement. Complementary events, A and a dash. Together they form the entire sample space. So, P of A plus P of A dash equals 1. Nothing is left out. Perfect balance. What if we already know that an event has occurred? This brings us to conditional probability. It is written as P of a given B. It means the probability of A, assuming B has already occurred. Mathematically, P of a given B equals P of A intersection B divided by P of B, provided P of B is not 0. Example, if A is drawing an ace and B is drawing a red card, then P of a given B means drawing an ace knowing the card is red. If A and B are independent, then P of a given B equals P of A. Let's apply everything we've learned to an example. Suppose P of A equals 0.4, P of B equals 0.3, and P of A intersection B equals 0.1. Let's find P of a union B, P of a complement, and P of a given B, step 1. Using the formula P of a union B equals P of A plus P of B minus P of A intersection B, substitute the values. 0.4 plus 0.3 minus 0.1 equals 0.6. Step 2. Complementary probability. P of a dash equals 1 minus P of A equals 1 minus 0.4 equals 0.6. Step 3. Conditional probability. P of a given B equals P of A intersection B divided by P of B equals 0.1 divided by 0.3 equals 1 by 3. So we have our results. Notice how these values perfectly satisfy the logical rules of probability. Everything remains between 0 and 1. Let's wrap up today's lesson. We learned that an event is simply a subset of the sample space representing outcomes we care about. We explored different types: simple, compound, impossible, and certain events. Then we learned how to combine events through union, intersection, and complement, using the key relation P of a union B equals P of A plus P of B minus P of A intersection B. We also saw how events can be independent, dependent, or complementary, and how conditional probability links them. Finally, we solved a complete example to bring everything together. Remember, event equations are the grammar of probability. They let us describe how different possibilities interact. Now, keep practicing, stay curious, and never forget, every probability starts with an event.